Hello everyone, and good morning or good afternoon, depending on where you are joining us from, and welcome to today's webinar. My name is Annabelle Chaplin from the Business Review, and I will be your host. It's our pleasure to have Evoqua Water Technologies with us today, who will be discussing new US ELGs and CCRs regulations, conserve capital, lower future operating costs, and ensure compliance. Today's guest speakers are Chuck McCloskey, the Director of Industrial Wastewater Services, and Mike Riff, the Industrial Application Engineering Manager. But now, please allow me to welcome Chuck McCloskey.
Thank you. On today's call, we will review some of the key features of the new Effluent Limit Guidelines, commonly known as ELGs, and in particular, the impact on flue gas desulfurization, scrubber purge, or discharge streams. Additionally, we will look at coal combustion residuals, known as CCRs, and how that will impact future pond closures. In both cases, we will present information on current and developing treatment technologies, as well as relevant case studies and successful applications. The EPA has implemented new regulations for coal-fired power plants designed to reduce the discharge of certain contaminants to the nation's waterways. This 81-page regulation, published in late 2015, addresses 8 different water streams commonly associated with coal handling and coal burning facilities. Sites that have implemented flue gas desulfurization for air pollution compliance will face new restrictions on the scrubber purge or blowdown water, most notably for arsenic, selenium, mercury, and nitrates. Another major change will be the elimination of discharge from ash sluicing operations. This table shows the specific new limits for FGD wastewater. Per the EPA, these new restrictions are designed to reduce the release of toxic substances to both surface water and municipal treatment facilities. It's worth noting that these are the minimum federal standards, and that state and local restrictions may even be tougher. At the same time as meeting these new limits, power plants will also have to eliminate discharge from fly ash conveyance streams. This will certainly affect the overall plant water balance and create new challenges for water management, water treatment, and operations. The water balance for a coal-fired power plant can be quite complex. This is a simplified drawing of the key waste streams. Mike will discuss the FGD wastewater treatment process in more detail.
Prior to September 15th, where the ELG guidelines came into effect, a typical FGD wastewater treatment plant would primarily consist of a physical chemical treatment process or a settling pond for desaturation of the gypsum and precipitation of some of the heavy metals. However, depending upon the ultimate point of discharge, local NPDES permits may be a little bit more stringent and require total nitrogen reduction or COD, BOD reduction through a secondary treatment process. Now that we have the ELG regulations in effect, a FGD wastewater treatment plant can and could consist of 3 treatment steps: primary, secondary, and tertiary. The secondary portion for total nitrogen reduction or BOD-COD reduction really plays a part on several factors. Number one is what the NPDES discharge requirements are for that particular utility, or if we had elevated nitrate concentrations in the waste stream. The key considerations for an FGD wastewater system in terms of the design, of course, are the influent compositions, the discharge requirements, ELG plus local, the solids handling, materials of construction, and each utility may have a unique requirement in terms of specific instrumentation or control systems. The major cost drivers for an FGD wastewater treatment plant are the flow rate, the solids handling, and specific discharge requirements for selenium, arsenic, mercury, BOD, COD, total nitrogen, nitrates, what have you. In terms of the solids loading, it's probably the biggest impact in the cost. In terms of FGD wastewater characteristics, the contaminants are primarily from the coal source or coal blend, the limestone used in the absorber, and also the makeup water. The net impact is on most FGD systems is you're going to have high TDS concentrations, high TSS concentrations. You'll have elevated heavy metals. Typical pH range is 5 to 6.5. The purge stream is going to be supersaturated with gypsum, which is extremely scale forming. The elevated chloride concentrations that we've seen on the facilities that we've executed have ranged from 10,000 to 50,000 milligrams per liter, which, because of that high chlorides, can greatly impact the material of construction, not only for pumps and piping, but also for instruments that come in contact with the waste stream. The nitrate, nitrites, and ammonia concentrations have varied widely. If a utility is using dibasic acid for enhancing the scrubber performance, there would be an impact on COD in the purge stream. Typical ranges are between 500 to 1,000 milligrams per liter. Typical FGD purge streams range in 105 to 130 degrees Fahrenheit. The next table is typical wastewater characteristics that we've seen in projects that we've executed, projects that we bid. TSS concentration, I'm going to only focus on those that are highlighted in red right now. I believe you'll be given a copy of the presentation and you can look at each value. But in terms of TSS, the ranges that we've seen have been 6,000 to 40,000. These higher ranges have been more specified than actual. The impact there is pretty dramatic in terms of the sludge handling and the sludge dewatering requirements. Of the 15 plants that we've executed, all but one have been less than 1% by weight, more in a range of 8,000 milligrams per liter. We've had one facility that was right around 1.5, 1.6. The impact is, like I said, a lot of extra capacity in your sludge holding and dewatering impacts. Chloride concentrations, again, 10 to 15,000 impacts material of construction for just about any component that will come in contact with the purge stream. Nitrates and nitrites have really been very wide. We've seen as low as 5 milligrams per liter to as high as 100 milligrams per liter. In terms of effluent quality, the values in red are the current ELG regulations. The first value is the current 30-day average. The second value is EPA's long-term goal. And as you can see, the effluent quality is becoming more and more stringent for FGD wastewater plants. A typical physical-chemical plant, treatment plant for FGD purge stream would consist of flow equalization, two-stage reaction, followed by clarification, pH adjustment, and gravity filtration. The concept that we utilize for the PhysChem plant is to operate the reaction trains at a fairly high solids concentration. We utilize the clarifier underflow, recycle it back to reaction tank number 1. We typically operate at 3 to 5% by weight in reaction tanks 1 and 2. Within reaction tank 1, we add the hydrated lime slurry along with the organosulfide. Some early versions of the process consisted of 3 stages where we added the hydrated lime and organosulfides in separate tanks. Through some R&D work, we determined that we could obtain the same performance by adding it in the same reactor. So we reduced it by 1 unit process. Typically, by operating at 3 to 5% by weight within the reaction trains, we can generate a clarifier underflow solids concentration of anywhere from 11 to 15%. We've had a few that are even higher, only because they're operating the reaction tanks at slightly higher concentrations. Typically, for a 400 GPM system with 8,000 milligram per liter of TSS in the influent, you're going to generate about 51,400 pounds of dry solids per day. And because that we are obtaining a high solids concentration in the underflow, there's no need for a conventional type thickener for concentrating up the solids. You'd simply need a sludge holding tank, which is equipped with an agitator for keeping the solids in suspension. And in terms of dewatering, the best success that we've had is utilizing plate and frame filter presses. We're able to achieve a density of the solids of 90 pounds a cubic foot and a cake dryness coming off of the press of typically greater than 50% by weight. Following the clarification process, let me back up. In terms of operating conditions within the reaction trains, we're operating at a pH of 8.5 to 9.2. And after the clarification process, we want to reduce the scaling potential, so we're utilizing hydrochloric acid to lower the pH slightly below neutral. The reason we've selected hydrochloric versus sulfuric is that FGD waste streams typically have high sulfate concentrations. So if you're adding hydrochloric or sulfuric acid, you would increase the sulfate concentration of the waste stream. Several of the systems that we've installed discharged into the Chesapeake Bay, so we had a total nitrogen limitation of 4 milligram per liter. The process that we selected was the utilization of sequential batch reactor technology. Because FGD waste streams have elevated temperatures and you're operating total nitrogen processes in a mesophilic condition, you want to reduce the temperature to an optimum of right around 88 degrees Fahrenheit. Through plate and frame heat exchangers, we would cool the liquid coming in from the physical chemical plant through plate and frame heat exchanger using a cooling source and transfer that flow into a SBR influent equalization tank. An SBR is a batch cycle, and it is utilizing anoxic conditions. We try to maintain a negative ORP of right around 250, minus 250. We selected the SBR technology because influent streams at various plants can change depending upon the coal source. So with a sequential batch reactor, you have a little bit more flexibility. The process of an SBR is fill, react, settle, decant, and idle. during a decant cycle, we're transmitting the treated effluent to an effluent equalization tank. It's a high flow for a short duration, so that levels the diurnal flow to the downstream treatment processes at a more constant rate. When we have implemented the total nitrogen reduction in an FGD system, from the PhysChem plant, we would take the filtration step and move it downstream to the SBR for final filtration. The tertiary step for removing of metals such as selenium, enhanced mercury, so on, typically can be fall into two classifications: biological or physical chemical. A few examples of a biological processes are a packed bed reactor, fluidized bed reactors, or a moving bed biological reactor. In terms of physical chemical processes, it's through reduction, and we typically on those kind of applications are using a zero valent iron technology. You could also consider ion exchange, but typically FGD has so many other background things that ion exchange hasn't been that successful for producing the levels of selenium, mercury, arsenic that ELG requirements dictate. We have a case study to provide to the group today, and this particular facility was installed in 2007. It was provided to Duke Energy. The project location is Belews Creek. I'm sure many of you listening in have read a lot of papers about Belews Creek. It's a very successful plant. Evoqua did it under a consortium agreement, and it was design build. The particular facility consists of physical chemical filtration, heat exchangers, and selenium reduction utilizing AB-MET technology. In the early days of that technology being developed, we were working with the original inventor, which subsequently sold to Xenon and now resides with GE. That particular application, we basically bought the rights to use the technology. We designed and built all of the internals, control logics, and everything else. A few items that I'll mention on this particular application is Duke Energy wanted some form of redundancy, and on several things, on several parts of the system, we developed some unique technologies. In the front of the picture, next to that construction trailer, you'll see 3 circular white tanks. In lieu of having 2 equalization tanks and 2 sludge tanks, just to let you know, the equalization tank is on the left-hand side. The sludge holding tank is on the right-hand side. In lieu of having 2 of those tanks, we came up with a novel idea of having all 3 tanks, all identical, with the center tank being classified as a maintenance tank. If the equalization tank needed to be taken out of service for inspection or change out of an impeller on the mixers or anything like that, we can divert the influent to the center tank, the maintenance tank, modify the influent valving to draw suction from the center tank, and then it would feed the PhysChem plant. Likewise, if the sludge holding tank had to come out of service, we could then utilize the center tank as the sludge holding tank. A few other unique features about this is on the right-hand side of the photograph, you'll see in the yellow building sort of a darker color at the lower level. The design of the facility allows for sludge dewatering trucks to come in on one side and drive out the other. So it's very convenient. It's substantially safer than having trucks back up and move forward. So very nice feature at this particular unit. In the background, to provide further levels of redundancy, we have a single train of reaction tanks, but two 100% clarifiers. They're the big, large tanks in the diameter in the back. The project was very successful. We performed. We're currently operating that facility. We've operated it from day one. What was unique about it is the system operated very well, and Duke actually waived the performance guarantee testing requirements because they were watching it, and it exceeded everyone's expectations. Now I'm going to talk about the tertiary step in terms of basic ZVI technology. How does it work? What is it? Zero valent iron is commonly known as ZVI. ZVI is elemental or pure iron. ZVI spontaneously reacts with many compounds such as axions, metal cations, and some organic molecules. The mechanism is somewhat complex, but it's a redox reaction with the ZVI acting as the electron donor, and immobilization occurs through surface absorption on the iron oxide, and it produces a iron corrosion. Historically, ZVI has had some issues. Primarily, it would rust out and it reacts. The reactivity is classified as passivization. It caused plugging of columns. There were many solutions tried to prevent the passivation from occurring, such as acidification, frequent backwashing, packed beds, even nanoscale ZVI. But until recently, there really hadn't been a solution found. What we have done is we have actually conditioned the ZVI, or zero valent iron, and we form a magnetite coating which prevents that passivization. The redox reaction goes after many axions, heavy metals, such as nitrate, selenium, molybdenums, chromate, silica, arsenic, copper, and mercury. Arsenic and mercury occurs very rapidly within a reactor, and it occurs through surface absorption. In addition to copper and mercury, cadmium, nickel, zinc, thallium are also reduced. A typical advanced zero valent iron reactive media system we've termed Puradox for the removal of metals and other trace contaminants consists of a 4-stage reactor. And we are adding anti-passivization reagents to each one of the tanks to maintain the ZVI. The reactors are basically a tank in the tank. The inner tank serves as the reactor. The outer annulus area forms as a quiescent zone to keep the ZVI within the reactor. Following a typical FGD application, by the way, consists of 4 stages. We provide a means of bypassing any of the reactors should one of the reactors need to be taken out of service for inspection and or maintenance on any of the agitators. Following the 4th stage, we transmit the flow and it is a gravity flow system. We gravity flow to an oxidation tank. What we're doing in the oxidation tank is we're converting the ferrous to ferric, which subsequently will precipitate out. We're doing that oxidation through aeration. Very simple. We do add a polymer to the clarifier. the solids that would be settled out in the clarifier, which is roughly going to be about 30 to 40 milligram per liter, would be transmitted to the sludge dewatering system of the phys-chem plant. Following clarification, we would typically utilize filtration. Filtration can be a number of different technologies. It can be continuous backwash gravity, multimedia, and even membrane filtration. One of the things I'd like to mention before going on here, there's been some talk about providing softening in the phys-chem plant, and we've installed one plant that has softening capabilities. One of the things that happen when you're softening, you're going to generate anywhere from 2 to 2.5 times the sludge that you would typically produce. So in a 400 GPM system, in a conventional FGD, you're going to produce about 51,000 pounds. If you were softening, you're going to generate anywhere from 102 to 128,000 pounds of dry solids a day. The density is going to be pretty much the same, 90 pounds a cubic foot. However, the capability of dewatering softening is substantially less than conventional FGD wastewater. Our experience has been anywhere from 22 to 28%. So if you used an average of, say, 26% dry cake, you're basically talking about 3 to almost 5 times the volume of sludge. So it's pretty dramatic on the sludge dewatering system. An example case study of the Puradox process. We have an ongoing system that is being tested at a East Coast utility. The design on the facility is 20 GPM. The results from this ongoing testing has resulted in proving out that the Puradox process can meet the ELG regulations based on a 30-day continuous performance, not only in arsenic, mercury, also nitrates and selenium. The chart that's accompanying this slide, a little hard to read because of the scale, but you can see the influent levels are in blue and the treated effluents are in red and far below the line in which the ELG regulations, which is going across horizontally. The chart also shows that we're operating at different flow rates. As we increase the flow rate, we actually got a higher degree of removal through the system. Still looking at that. I know one of the questions is going to come up, well, how much ZVI is required in a system? It really depends on several factors, flow rate, of course, the concentration of selenium, also the concentration of nitrate. Typically, order of magnitude on a conventional type FGD system, based on having around 25 milligram per liter of nitrate, you're looking at a range of 250 to 400 milligram per liter of ZVI for dosage rates. If the system had a low nitrate or we installed a total nitrogen or a nitrate reduction system ahead of it, the consumption rate is reduced by roughly 70%. So in lieu of 250 to 400, you're looking at 75 to 120 milligram per liter. So, and ZVI is relatively inexpensive. Unconditioned, it's roughly about 60 cents a pound. In summarizing the physical, chemical, and total nitrogen and polishing effects, like I said, the influent composition of the waste stream greatly impacts the design. Discharge requirements, of course, depending on what the local NPDES permit requirements can greatly impact the design requirements of the system also. Sludge handling, I think that's really the key aspect of an FGD system design. We've done 15 facilities, and a lot of them have been over-designed in terms of the solids handling, only because when the design was done, they were looking at various different coal sources, and they would take the worst of each one of those coal sources, and instead of designing for less than 1% or 1%, it's typically been up to 4%, which is dramatic over design. Material constructions, I can't stress that enough, that you really need to take in consideration what the chloride concentration is, what the right metallurgy is going to be, or wherever possible, use non-metallic. Owner's unique requirements. Everybody has their wish list. Some of them are redundancy, and that's accompanied by a lot of zeros. So if you take a look at the facility, as I mentioned, utilization of maintenance tanks are ideal. Typically, all the rotating equipment, one operating, one standby, or N+1's the best way. In terms of best available technologies, physical chemical, it's got to be designed right. Otherwise, you're going to have a lot more unit processes. We really utilize the solids in the waste stream to help desaturate the gypsum, obtain high solids concentration in the underflow, which subsequently results in high dry cake coming off the filter press. In terms of nitrate or total nitrogen reduction, that's going to be a requirement each. We've been very successful of applying SBR technology to meet those requirements. And in terms of meeting the ELG requirements, we've proven out that the Puradox is definitely suitable for meeting that technology and limits.
Thanks, Mike.
You're welcome.
Thank you for concentrating on the FGD purge water and the ELG limits. Another set of regulations that are impacting coal-fired power plants is known as CCR, and that stands for Coal Combustion Residuals. It was promulgated from the Resource Conservation and Recovery Act, and it deals with the solid byproducts from burning coal, such as fly ash and bottom ash. Per the previously discussed ELG regulations, these materials can no longer be sluiced to an impoundment with an overflow for discharge. Dry handling or closed loop systems will need to be installed to move and dewater these solids. Many plants have combined use impoundments for ash, FGD purge water, and low volume waste settling. The discontinuance of ash sluice water flow to these ponds will change the plant's water footprint. Some plants will implement new FGD physical chemical treatment systems, leaving the current ponds largely inactive. Other plants that have been idled or repowered with natural gas will have ponds that need to be dealt with in the near future. Impoundments must be evaluated for several reasons. Location restrictions, if they're too close to a seismic area, a navigable waterway, an active aquifer, or a residential area, they may require closure. Also, ponds will need to be evaluated for structural deficiencies, including liner integrity. Groundwater monitoring will be required for ponds that remain in use. Certainly, a large number of ponds will require closure plans and actions to be implemented in the near future. The variables for pond closures are much the same as for any wastewater treatment application. Water quality in and out as dictated by the local NEPADES permit, the volume to be evacuated, and the time frame in which it needs to be accomplished. All discharged water will need to meet pH, total suspended solids, and oil and grease limits at a minimum. The free water at the top of the pond will be easily clarified and filtered with typical mobile water treatment equipment. Where tighter restrictions exist for metals or nutrient removal, more extensive treatment will be required. Activated media such as Puradox, wastewater ion exchange, and fine filtration may all be necessary to meet future limits. Let me give you a couple of case histories where treatment has been successfully put in place. A Midwest utility faced an emergency situation when heavy rains took their ponds to within inches of overflowing to the Mississippi River. A mobile clarification trailer was dispatched and operating within 48 hours. The added treated flow capacity lowered the water level to a safe point while consistently meeting their TSS limits. Another case involved a Midwest coal-fired facility where the runoff pond, again because of heavy rains, needed emergency treatment. Both TSS and dissolved iron needed to be removed, and mobile clarification and filtration were employed. Again, capacity was increased and compliance maintained. Several current projects are underway at this time that go even further, addressing arsenic, mercury, selenium, and nutrients such as nitrate. So what do our clients, customers, and operators need to do now? Start early. It's never too early to start planning. Pick knowledgeable partners, people that have experience in the industry and experience with these types of applications. Evaluate all of your options. Test your hypotheses and make critical decisions early so that implementation can match timing and performance criteria. Thank you for your attention this afternoon. The moderator will now open the question and answer portion of the webinar. Thank you again.
Okay, thank you very much, presenters. Audience members, it's now your time to ask any questions or comments that you have for either of the presenters today. So please do send some in for us. We do like giving you some feedback. Presenters, I'm just going to go straight in now to the first question that has been sent in today. And the question is, if you could select tankage, what would you use in terms of materials of construction?
This is Mike Reif. I'll handle this question. If the tank could be 14-foot diameter or less, it could be shop fabricated, and FRP construction is the logical choice. Anything above 14-foot diameter is going to have to be field erected because 14 is the maximum limit that you can ship over the road. It is expensive to ship 14, but with front and back exports, you can meet that. Above 14-foot diameter, like I said, is going to be field fabricated. There's a number of different options available. There are I believe they call them bow tie tanks where FRP, they ship them in modular sections and then erect it in the field. Other alternates are coated carbon steel or coated concrete.
Okay, great. The next question is, does the technology you operate at the Duke Energy plants you showed in the case study or similar plants consistently meet the new ELG limits?
The Duke Energy Belews Creek is very good performance, but it doesn't meet the new ELG regulations in all parameters. I'm not sure about the arsenic. I haven't seen any results on that. In terms of the Puradox case study that we showed, yes, it does meet and is well below the new ELG regulations.
Okay, great. Thank you for that question. The next question is there a need for additional dewatering polymers after the sludge tank?
The answer is no, provided that you use plate and frame filter presses. If you were planning on using belt filter presses, I wouldn't recommend it based on my experience, but the answer would be yes. And the order of magnitude volume of polymer is going to be anywhere from 6 to 11 pounds of polymer per dry ton of solids to be dewatered.
Okay, great. The next question what's coming now is, what clarifier overflow rate would you select?
That's really subject to the design of the facility. If you were using 100%er or 250%ers or what have you, then order of magnitude is going to be about 0.35 GPM per square foot. The clarifier is solids contact. You want to have a solids contact versus just a conventional rate clarifier because of the high recirculation rate, and it better utilizes the chemistry. If you were designing for, say 260%ers or 270, again, you would look at around 0.35 GPM per square foot.
Okay, great. The next question is, can these systems handle ash transportation water flows, or can they be combined with SCR treatment?
Yeah, this is Chuck McCloskey. My understanding is that the ash transport systems will need to be closed-loop systems in the future and disassociated with the FGD water. There may be a chance to use FGD purge water as makeup to other systems and vice versa, but largely they will be disconnected in the future.
Okay, great. The next question is now, how fast can I get the mobile equipment on site for pond dewatering?
Usually within 7 to 10 days, but as we saw in the examples and case histories, this can be accomplished faster in emergency situations.
Okay, great. The next question now we're going to move on to is, should I use EPA recommended technology or BAT, best available technology?
This is Mike Reif. I'll answer that. It really comes down to how you would want to execute the project, having multiple vendors or one vendor providing a system-wide performance guarantee. I've been involved in executing the best available technology at 2 sites. Like I said, we had an agreement with Xenon and GE on those facilities. They work well. There are certain things that are different about it. One of the things that the big difference that I see, would I do it over? Are there things I do? Yeah. I would definitely, if I were using the AB Met technology, I would definitely cover the tanks and have vapor collection and vapor treatment on the system because it does generate hydrogen sulfide gas, and to an extent that it's prevalent or a safety issue. We operate the one facility in Belews Creek that has it, and we basically sound an alarm before we backwash the beds to make sure that there isn't a safety issue. Yeah.
Okay, great. We'll go straight into the next question now. For the Puradox technology, what kind of pre-treatment would be required? Would a typical physical chemical system be necessary?
Yeah. Go ahead, Mike. We're going to talk about the difference.
Yeah, I mean, if the existed, there's not going to really be any new coal-fired power plants built right now because of the expense of it. But if, the existing facilities that have FGD, they're either going to have, ponds, or they may already have a physical chemical plant on it. The ponds will work very well for reducing the TSS and conditioning the stream that you could go directly from the pond to the Puradox system. The only thing I'd say is we'd probably want to look at it case by case in terms of what is the TSS that's going to come to the Puradox. The issue that I have with high TSSs there is it sort of gives you a false reading if you don't monitor the influent TSS, but you're monitoring the concentrations of ZVI. You may not be able to really find out, okay, how much is influent, TSS, and what is the concentration of the ZVI without further testing. So, but to answer the question, PhysChem or a pond works fine.
Okay, great. We'll go into the next question now. What is a good starting point for organosulfide and ferric chloride dosages?
This is Mike Reif. We found that if you overdose the organosulfide greater than 10 milligram per liter, that you're wasting the chemical. Likewise, if you substantially overdose the organosulfide, it can impact a downstream biological system such as ABMet. Organosulfide has toxicity limits on it. In terms of ferric chloride, it's really a matter of doing some jar testing, but it's going to be anywhere from 50 to 75 milligram per liter.
Okay, great. I'll go into the next question now. Audience members, we do have a little bit of time left, so if there's any last minute questions you want to send in, now is the time to do so. But I'll take us into the next question now. For the Puradox design, what was the ZVI consumption per gallon treated?
It's going to work out depending, if you had an influent nitrate concentration of 25 to 30 milligram per liter, the dosage rate's going to be about 250 to 400 milligram per liter. If your nitrate concentration is, say, 5 milligram per liter or less, it's going to be roughly 70% of that, or 30% of that, so 75 to 125 milligram per liter.
Okay.
And of course, the amount of selenium will also impact it.
Okay, thank you. The next question is there an incentive program for zero liquid discharge, ZLD?
This is Chuck McCloskey. Yeah, there is an incentive program in the regulations. It allows for delay of implementation to 2023 if this option is selected and selected early. The cost for ZLD treatment are still being determined, generally requiring thermal energy for evaporation, but that option is available for operators to consider.
Okay, great. Audience members, thank you for all your questions and comments there. If we didn't manage to get back to you, I'm sure the presenters will be more than happy to, at a later date, and even respond to you with a more detailed response. But before I conclude, presenters, is there any final words you'd like to leave us with today?
I just thank
I
you for
appreciate
everyone for
everybody attending.
Yeah.
Hey, good minds think alike, Chuck.
Okay. So again, that just leaves me to thank Chuck McCloskey and Mike Rife for what was a great presentation, and to also thank Evoqua Water Technologies.